Okay, good morning everyone. So myself Deobroto Kumar Das from Dumka Engineering College. Today 24th January 2022, and today we'll discuss the subject is control system. Topic is gain margin and phase margin.
Okay, good morning, everyone. Am I audible?
Good morning, sir.
Okay,
Good morning, sir.
okay. So we start. So last classes we have discussed in our stability, that is the Bode plot. Okay, and also we have to certain discuss that is the root locus method. So I think all of you read these topics in carefully. I am uploaded the class note in your Google Classroom portal. So in according these topics, these are the basically it is formed in our stability analysis in our control system. So there are certain another topics is available. So we have to cover today also, that is a gain margin and phase margin also. Okay, so wait, I am sharing my whiteboard. So my whiteboard is visible, everyone.
Yes, sir.
Okay. So today is a gain margin and phase margin. So let us start. So we have to also cover in our Nyquist criteria, in our stability analysis in our control system. So in this stability criteria in the Nyquist plot, where we have to calculate the proportional constant, that means the K. So K is the basically basic important term when we have to cover in our Nyquist plot. Okay. So this proportional constant or integral constant or proportional derivative controller or PID controller, we have to express here, that is the K, and then Ki, that means the for integral controller, then PD, that is the proportional derivative controller, then also PID, that means the proportional integral and derivative controller part. So in this regarding, we have to discuss in three states of our stable system. That is a stable system also. Next, that is a marginal stable. Another one is the unstable system. So we write the three condition of our stability. So first one, that is the when the value of k, it is less than 1 by t1 plus 1 by t2, then this system, it is called the stable system. Okay, so please remember these things also. We have to solve in our different examples in the previous classes also. So these are the basically first one, that is the stable system. So here t1 and t2, these are the basically different time scale. So first consider when k is less than 1 by t1 plus 1 by t2, then the system, it is called the stable system. Okay, next another condition we have to learn, when this is k is equal to 1 by t1 plus 1 by t2, then the system, it is called the marginally stable. Okay, is marginally stable. Okay, and another number 3 conditions we have to learn. When the value of k is greater than 1 by t1 plus 1 by t2, the system it is called the unstable. Is unstable. So this 3 part we have to learn in our previous more classes. So when the value of proportional constant it is less than the 1 by t1 plus 1 by t2, these t1 and t2, these are the different time response in our control system. So in these conditions, this is called the system, it is called the stable position. Okay, and when the value of k is equal to, that is 1 by t1 plus 1 by t2, then the system it is called the marginally stable. And the another one, when the value of k is greater than these timing cycles of this system, it is called the unstable system. And when we have to plot, these are the basically we have to plot it the Nyquist plot in the corresponding response, then the system it is showing in that pattern. Just wait, I am drawing one by one, then the system it is also basically what is a stable system or what is a marginally an unstable system. So first of all, this is the one real axis, another one is the imaginary axis. This is a imaginary axis and this is a real axis. So when the system it is k, it is less than this the timing cycle, that is a 1 by t1 plus 1 by t2, then the system it is called the stable system. So add in that point, that is the value of omega, this is also infinite region. And we have to know last classes, this omega is value, it is also present in the stable system, that is positive, that is a plus 0 to plus infinite. So in that case, these are the basically the point is 1 plus z0, and when the system it is stable, that means these are the basically region. These are the basically clockwise directions. Okay, according to these are the basically clockwise directions. So this is the omega. So when the system it is also stable, then the curvature of the stable system it is a lower part, that is a less than of the 1 by t1 plus 1 by t2. In that case, this system it is called the stable system. So when you have to express, you have to plot it this diagram. This is the t, and we have to express their output with respect to the timing. When the system it is stable, the pattern is showing in that pattern. Something like that. Okay, so this is the basically stable system. Okay, this is the figure A. When the system it is marginally stable. Next page. This is a real axis. This is a imaginary axis. This is a real axis. And in that point, it is also we have to express the omega, it is region, that is a plus 0 to the infinite, plus infinite region also. So these are the basically next one when the system it is also marginally stable. So these are the basically point here we have to that is 1 minus 1 plus 0. These are the basically point. And it is also clockwise direction. This is the omega. So previous diagram here you can see this point it is also below part of the this section also. So that means in that case, we have to tell here K is equal to 1 by T1 plus 1 by T2. That means sometimes it is also stable, sometimes it is also now not stable. So that's why it is called the marginally stable. So we have to plotted the graphically responses. This one. This is time. This is the output of the response. Something like that. So these are the basically stable region we have to pick, and sometimes it is also stable and sometimes it is also unstable. So these are the system it is called the marginally stable format. Another one, last one, when the system it is unstable. So when the system it is unstable, that means here the value of K it is also greater than the 1 by T1 plus 1 by T2. So this is the imaginary axis, this is the real axis also, and this is the center point where the omega is also infinite. So here you can see this is the something like that. So this is the basically point of -1 plus J0, and where the point is located, that is the outer side of the region. That means greater than K is greater than that is 1 by T1 plus 1 by T2. Okay, so then the system it is called the unstable format. What is the graphical structure? So these are the basically output. Another one it is also with respect to the timing. This is output of the system. So it is started from the center point 0, then it is also gradually increases, then also this system it is not stable. That means that when the timing it is also not stable, so the output it is also variable in the fluctuates in the different points also. Okay, so then this system it is called the unstable format. Is it clear all of you? So this is the basically Nyquist plot and corresponding step response. Is it clear all of you? So please remember, please tell me. So we have to calculate the stability of the system, of the value of the different stable system. That is, one is a stable system, another one is a marginally stable, another one is the unstable. Is it okay?
Yes,
Is,
sir.
is response everyone? Okay. So next we have to calculate the gain margin and phase margin from the Nyquist plot. Okay. Gain margin and phase margin from Nyquist plot. So we have to learn in our previous three diagrams. One is stable and marginally stable and unstable format. So in that case, we have to also draw one figure. This is the real axis. Another one is the imaginary axis. So here the system, it is stable. So when this is stable, something like that, this is the pictures. And another one, this is the point of -1 plus 0. And this is the unit circle. Something like that. Sorry. Not that pattern. This is the connection point. I am coming one by one. This is the angle of phi, and this is the omega of plus infinite region. And also this is also the clockwise directions also. And it is connected from the center point to the this point also. Okay, so I am coming one by one. This is called the unit circle. This point where the real axis we have to touches the first one, this point. This point it is called the phase crossover frequency. Phase crossover frequency, and we have to express here omega 2, this point. Another one, this point, this is connection to the real axis, this point. This is called the gain crossover frequency. Gain crossover frequency with respect to, we have to express here omega 1. Okay, this is the omega. So this is the basically pictures of the gain margin and also phase margin. We have to plot it in our Nyquist plot. So when the system, we have to know when the system, that is the value of k, it is also ranges between the -1 plus 0, then this system, it is called that is a stable system. When this position, that is the frequency, it is also touches this point, this system, it is either it is called marginally stable. Okay, that means sometimes it is also stable or unstable format. And when the value of k, it is cross this region, that these are the basically cross this region, then the system, it is called the unstable format. So in this view, we have to plot the Nyquist plot. So the Nyquist plot for a stable system is shown in figure. This is the figure A. This is the basically gain margin. And phase margin from Nyquist plot. Okay. So this Nyquist plot for a stable system in the figure A, the plot cross the negative real axis at omega equals to, that is the omega 2, and the corresponding magnitude we have to written here mod of j omega 2, also feedback, that is h j omega 2. Okay, it is less than also 1, less than 1. Okay, so in this case, you have to remember this Nyquist plot for a stable system. That means the region, it is also k is less than 1 by t1 plus 1 by t2. So this stable system, it is plot the cross the negative of the real axis at the omega, that is equals to, that is the omega 2. This omega 2 we have to express here phase crossover frequency. Okay, and another one, this value, it is also we have to calculate the magnitude of the Nyquist plot. This is expressed as g j omega 2 h omega 2, and its value, it is always less than 1 for the stable system. And another one, when this value of magnitude of g j omega h j omega equals to 1 at this point, so we have concluded that if the gain is increased by factor that is 1 by g j omega 2 into h j omega 2, the closed loop system becomes unstable. Okay, so this is the basically point when this value of this magnitude of the g j omega h j omega, it is basically equals to the 1. At this point, we have to conclude that the gain is increased by the factor of the 1 by this magnitude. When this closed loop system, it is become also unstable. So at this point, there exists a margin of the increasing of the gain of the system is available, where the frequency of the omega 2, that is, this is also frequency, this is the gain crossover frequency. So when this frequency is omega 2, at which the Nyquist plot it across the negative real axis, and it is termed as the phase crossover frequency. And the starting point here, the omega, it is also connected to the negative region to the positive real axis also. This frequency it is called the gain crossover frequency, and this gain crossover frequency we have to express here omega 1. So we have to tell what is the basic definition of the gain margin. So the gain margin is a factor by which the gain of a stable system is allowed to increase before the system reach, reaches instability. Okay, so this is the basically one sentence of the definition of the gain margin. The gain margin is a factor by which the gain of a stable system it is allowed to increase before the system reaches the instability point. Okay, so this gain margin we have to this gain margin it is expressed as expressed in decibel. Decibel. This is the unit that is a D and B also. So we express the equation that is gain margin. This is equals to 20 log 10. This is 1 by magnitude that is G j omega 2 into 8 j omega 2. This is the more. This is decibel. Okay, so this is the basically a gain margin. So what is the gain margin? So this gain margin, it is a factor by which the gain of a system, it is also stable system. It is allowed to increase the before the system when it reaches the instability point. And this gain margin, it is expressed in our control system. It is decibel. This is expressed dB also. And this is the expression Gm, that is a gain margin. This is equals to 20 log 10. This is a 1 by mod of, that is a magnitude, 1 by G j omega 2 is j omega 2. It is expressed in the unit of the decibels also. So for stable system, so it is clear all of you?
Yes, sir.
So when the system it is also stable, that is a for stable system, we tell that that is magnitude G j omega 2 H j omega 2. Its value is less than 1. The gain margin is decibel is positive. Okay, this is the one condition, number one condition. Number two, for marginally stable. Marginally stable system where the magnitude that is equals to 1, then the gain margin is also expressed in decibel, it is also 0. And number third, we have to tell for unstable system, where the magnitude g j omega 2 and h j omega 2, this is also greater than 1, then the gain margin is decibel, it is also negative. Okay, is it clear, all of you? So you have to remember these things also, these three conditions also. When the magnitude it is greater than, sorry, less than 1, then the system gain margin it is also positive in the decibel unit. When the magnitude it is equals to 1, in this case the gain margin it is equals to the 0, and the magnitude it is when greater than also 1, then the system it is also negative, and then this system it is called the unstable system. Okay, is it okay? No one
Yes,
is
sir.
response. Okay, thank you. Next, another terms is the phase margin. Okay, at this phase margin we have to express here Pm. So the definition is the phase margin of a stable system is the amount of additional phase lag are required to bring the system to the point in instability. So this is the basically one sentence that is a definition of the phase margin. So this phase margin of a stable system, it is the amount of the additional phase lag required to bring the system to be the point in the instability format. So in that case, in the previous diagram, we have to plotted the Nyquist plot of the given system, and here phase margin we have to express, that is a phi, angle of phi, it is also positive. Okay, you have to go the previous diagram. So this is the basically phase angle. Okay, this is the basically phase angle where we have to express that is a phi also. Okay, so this phase angle it is also positive for the stable system. We have to plot it in the Nyquist plot also. So in that case, open loop transfer function, the open loop transfer function at omega, we have to express here omega equals to, that is omega 1, that is also angle of g j omega and also h j omega 1. So this is the open loop transfer functions where the omega that is equals to the omega 1. We have to express that is equals to angle of g j omega and h j omega. So what is the basic equation? So the phase margin is given by, we expect that is the PM, that is the phase margin. This is equals to 180 degree plus angle of the magnitude, that is the g j omega h j omega. And also here one condition it is also present, this angle of the magnitude g j omega and h j omega is being measured in clockwise. Measured in clockwise. Okay. So I'm conclude this also phase margin. This phase margin we have to express here P dot M, that is the phase margin. This phase margin, it is basically stable system, is the amount of the additional phase lag system it is required to bring the system to the point in the instability format. Okay, so when this criteria we have to plot it in our Nyquist criteria in the previous diagram we have to show. So here the phase margin, that is the one phase angle we have to draw. This phase angle it is expressed, that is a phi, and it is also positive in the stable system also. So when the phase angle it is also positive, then the system it is also called the stable system. So in that case we have to express the omega, that is equals to omega 1, and the angle of magnitude, that is the g angle of g j omega is j omega also. So what is the basic equations of the phase margin? That is PM, that is equals to 180 degree plus angle of g j omega is j omega, and also it is this angle you have to measure in the clockwise directions also. Okay, so this frequency of omega 1 at which the Nyquist plot, it crosses the unit circle, it is known as the green crossover frequency. In the previous diagram here you can see we have to express here two things. One is the phase crossover frequency. This phase crossover frequency we have to express omega 2. Another one is the gain crossover frequency. We have to express here omega 1. Is it clear, all of you? This is very important topics in our stability system. Okay, is it clear?
Yes, sir.
Okay, so everyone please write
Yes.
your own name and roll number in the chat box also. And Gautam is present. Okay, Sandeep, are you hear me?
Yes, sir.
So you take a screenshot of the participant list, okay? And
Okay, sir.
after ending the class, you have to send me. So this is the basically gain margin and phase margin of the Nyquist plot. So when you have to solve the Nyquist problem, Nyquist criteria problems in the stability analysis of the control system, so you have to also calculate the gain margin and phase margins also. Okay, so this is the basically Nyquist plot of the one given format. So these are the different region. So first you have to calculate the gain margin. This gain margin we have to express here 20 log 10 equals to 1 by magnitude, that is the g j omega 2 plus g j omega dot h j omega 2, and here omega 2 it is also expressed here also phase crossover frequency. And when we have to consider the phase margin, we have to consider the gain crossover frequency of the omega 1. So this is the basically equations of